Good afternoon, and thank you for joining us today for the NEA webinar on Accident Tolerant Fuels, Prospects and Possibilities. Opening remarks today will be made by Mr. William D. Magwood IV, NEA Director General, followed by a presentation of the report from Dr. Kamal Pashamemamet Olu, who is the Versatile Test Reactor Executive Director at the Idaho National Laboratory and the Chair of the expert group on accident tolerant fuels for light water reactors, which produced this report. He will make his presentation by video link. We'll then take questions from the audience, both here and online. Our on-stage panel for the discussion is Marie Moati, who's the Senior Executive Advisor on Nuclear Fuel Safety and Economics at Électricité de France, EDF, and who is a key contributor to this report. She led the work on cladding designs. Marc Verwerft, Head of the Fuel Materials Group at the Belgian Nuclear Research Centre, that's the SCK-CEN, who also contributed to the report, is here today representing the European Nuclear Society. Next to him is Tatiana Ivanova, who's the head of the Division of Nuclear Science at the NEA. And joining them all by video link is Masaki Kurata, who's the Division Leader of Fuel Debris and Core Status Evaluation Division at the Japan Atomic Energy Agency. And he led the report on fuel design in this report. And they will all do their best to answer your questions. And you can send us your questions via Twitter to the handle @OECD_NEA or by email to press@oecd-nea.org. It's now my pleasure to give the floor to Mr. Magwood.
Welcome. Thank you for joining us for this important webinar on the state-of-the-art report on accident-tolerant fuels for light water reactors. This is a report that's gotten a lot of attention from many sectors of our nuclear society, and we're pleased to be here today to introduce it to the audience that joins us on the web from around the world. As you know, there are nearly 400 light water reactors around the world in operation or under construction. These reactors provide more carbon-free energy in NEA countries than any other source, operate reliably year-round, 24 hours a day, 7 days a week, for 40, 60, perhaps even 80 years. The heart of this technology is a fuel. Fuel which for many decades has been composed of uranium oxide pellets clad in zirconium alloy. The global industry has refined this fuel technology over the course of many years, and it's now today a very safe and reliable technology that supports the excellent long-term operation of nuclear power plants around the world. However, in the aftermath of the Fukushima Daiichi accident, companies and research organizations around the world have been searching for ways to make this already very good fuel even better. In the years after the accident, nuclear plants in all countries have been made more resilient in the case that they are confronted with unusual natural events such as large earthquakes or floods or tsunamis. The work that we will discuss today has been focused on also making the fuel more resilient. These technologies are collectively known as accident-tolerant fuels. To review the state-of-the-art of the development of these advanced fuels, the NEA established the expert group on accident-tolerant fuels for light water reactors, working under the auspices of the Nuclear Science Committee. This expert group brought together representatives from 35 organizations, R&D organizations, nuclear operators, fuel vendors, academia, technical support organizations, research and test reactor operators, all from 15 countries around the world, and observers from the IEEA. The expert group's work focused on reviewing and evaluating currently available knowledge on cladding and fuels with enhanced safety and performance characteristics. Their findings are summarized in this report. The report identifies the potential benefits of each concept and the remaining development required for successful deployment. The report also provides expert opinions on the technology readiness levels of different options, data gaps, and the potential difficulties for each technology. The objective of this assessment is not to choose winners or losers, but to provide a set of evaluation criteria to guide the development of advanced fuels. These advanced technologies can enable higher levels of safety, greater performance, and improved economics. They are, therefore, of very broad interest. We hope this report will provide policymakers and stakeholders with internationally reviewed information that they can use as a basis for choosing the most promising technology that's consistent with their specific strategy, their business cases, or their deployment schedules. And we also hope that young researchers at the beginning of their careers will find this a useful reference as an overview for the scientific aspects of developing advanced fuels. Innovation in nuclear technology today requires coordination from all the actors in the sector. The NEA was founded to foster cooperation among countries to further research and to foster the deployment of new innovations. This report is our latest contribution to these efforts. So I'll now invite Kamal to provide you with a more detailed summary of the report and its findings. Kamal.
Me?
Yes, Kamal, we see you. Please go forward.
Okay. So I'll give you a very quick summary of the report, and obviously we are going to leave the details for questions and answers. Let's move on to the next slide, please. A little bit of the history. Right after Fukushima Daiichi, as Director General indicated, we had a couple of workshops to kick off the expert group in 2012 and 2013. Eventually, in April 2014, we have established the expert group, and we continued to work together until January of 2018, and the end result is the report that we have in our hands. We broke the expert group into 3 task forces looking at different aspects of the problem. A systems assessment task force, cladding and core materials was a separate task force, and the fuel concepts was a separate task force, but at the end the report was compiled by the entire expert group. Director General already indicated there were 35 organizations participating from 14 NEA member states as well as the Public Republic of China. And it had a mix of technical researchers, technical experts from utilities, fuel vendors, academia, and regulators. Next slide, please. The report is structured in 5 parts. The first part was evaluation metrics and illustrative scenarios looking at those metrics. Cladding and core materials. Part 3 was the fuel design. We did a first pass at evaluating the technology readiness levels. The definitions of those were provided in part 1. And then we looked at also at the cross-cutting items such as compatibility of the cladding and the fuels. As the Director General indicated, the objective was never either promote or criticize any one of those technologies. We addressed all the technologies that were being worked on by the different member states at the time. At the end, we tried to provide an objective overview of what the state of the art is and what additional work needs to be done, but did not go into ranking or prioritizing the value of any of the technologies. And another thing important to note is that the report is based on publicly available open literature data. We try to avoid, we did not have access to a lot of intellectual property proprietary data that the vendors might be developing, but we also try to avoid any speculations if the data is not publicly available. Next slide, please. in the first part, the evaluation metrics basically covers the fabrication, the normal operations, the design basis accidents, the design extension conditions, and the overall fuel cycle. And we have provided a consistent set of definitions for the technology readiness levels, a short overview of the fuel performance and systems codes, the modeling and simulation tools that can be used in the evaluation was provided. And also, in that section, in that part of the report, we have reviewed a high-level overview of any experimental facilities and experimental capabilities that do exist, and we try to highlight if there are gaps in there. Next slide, please. From Task Force 2 and Task Force 3, we basically looked at in the initial meetings, we made a list of all the different technologies that are being worked around the globe by the different participants of the expert group, and we looked at their attributes, tried to summarize the attributes of why such and such technology might be of interest. On the cladding and core materials, we have grouped them into 5 chapters. Coated zircaloy, advanced steels, that is high chrome, high aluminum steels that are of interest for oxidation conditions. We looked at the lined molybdenum alloy cladding, the ceramic cladding, silicon carbide composite cladding. In addition to cladding, there was some interest in at least a few of the member countries with respect to looking at materials that can be used for accident-tolerant control rods and for specifically for boiling water reactors, the channel boxes. So we added those as chapters into this cladding and core materials also. On the fuel side, we have grouped different types of fuels being developed into 4 categories: doped uranium oxide fuel, high thermal conductivity fuels with some additives, high density fuels, this is high fissile density, high uranium density, and encapsulated fuels. Then between the fuels and the claddings group, we looked at the compatibility in terms of thermal, chemical, mechanical, and neutronic properties between the cladding materials and the different fuels. And we have also made an initial pass that based on our expert judgment and publicly available data on where we think the technology readiness level is. So next slide, please. The next, I'll show you an example of basically a technology readiness level table. This one is for the cladding materials. Again, it looks at the different cladding materials and looks at the technology readiness levels in 4 categories in terms of irradiation behavior, fabrication, safety for normal operations, and the off-normal conditions. As you can see, in most cases, we are ranging somewhere between 2 and 5. 5 is specifically for zircaloy-based coated cladding materials. The other ones, non-zircaloy cladding materials, have a lower technology readiness level. Next slide, please. We have also looked at the compatibility between the different cladding and the fuel materials. It is color-coded, and of course the report itself does not show the colors, but I think with respect to the words that we put in the tables, color-coded tables, that it is kind of easy to see. potential showstoppers are shown by black, which we really did not have any of those. But red is kind of bad. It is a challenging area. Green is good. That we have enough data and we feel it's ready to go if one chooses to use that combination of cladding and fuels. Next slide, please. And this one is an example. As I said, this in colors, it's a lot easier to see than the report on the black, white, and gray scheme. But as you can see, this example is silicon carbide. It's no surprise that there's quite a bit of red, especially with respect to mechanical properties. So we do need quite a bit more data in that. But the blue and green also give us confidence that there are parts of it that they are fairly amenable to being able to deploy this cladding. Next slide, please. In summary, again, the objective was not to identify the best cladding material or the best fuel material that we recommend. We try to observe the general trends. In general, neutronically, we did not see many problems, even though in some cases the materials may require additional enrichment or higher uranium density fuels. In terms of the high fissile density fuels, there's still quite a bit of work to be done, especially with respect to chemical and mechanical properties. As I've indicated, the silicon carbide, due to the low ductility of the ceramic materials, we have to pay special attention to mechanical properties under different conditions. And data are still being collected in those areas. Overall, this was, again, the compilation of the report was the result of 3 or 4 years of research after Fukushima Daiichi. In most cases, there is still quite a bit of more data that needs to be gathered for the different fuels and cladding materials, with the emphasis that there may be other data out there that is not reflected in the group because they are vendor proprietary but in general there is need for more data. And I believe this will, I'll end my presentation here and open it up to questions. Thank you.
Thank you, Kamal. So we have a few questions to start with, and I think that one question I'd like to put to both Kamal, who I assume is still on the line, and our guest here on the stage, about an important aspect of this that came up quite frequently as accident tolerant fuels are first explored, which is whether they provide an economic incentive for the deployment. Do they provide operators with the opportunity to reduce their costs in a significant fashion? And I'd like to ask each of you to kind of address that and give us your thoughts about that. And perhaps, Marie, we can start with you.
Okay, so first, hello to everyone. I'm very happy to take part in this webinar, which is a very new experience for me, so I hope it's clear for everyone what I can say. With regards to cost, of course, it's a very important issue. There are several types of costs when you think about ATFs. Within the EGAT-FL, we have tried to work systematically about thinking on procurement fabrication costs and also, generally speaking, fuel cycle costs. For example, reprocessing, is it possible and at what cost? Frankly speaking, it's not, we have had most of the time, very qualitative approach. It's been rather impossible to put very specific numbers, but this qualitative approach is already very interesting. What can be said is that for rather evolutionary concepts, we can expect fabrication costs to be reasonable, like for chromium-coated claddings, but for other type of concepts, it can be much more costly because, industrially speaking, it's a brand new field for nuclear fuel, like, for example, SiC claddings. But we don't have to stop on just that type of cost. We need to think about expected performance. And here, the approach can vary a lot depending on the country and the safety referentials. You probably are aware that in the US, ATFs are also labeled as advanced technology fuel with high expectations in terms of cycle length, power rates, and in France it's different. In France, we don't plan to use ATFs for very ambitious, I would say, purpose. We are really focusing on accidental issues, and our referential, safety referential, for example, for LOCA is very specific, and we are really interested in fuels that will prevent ballooning, because this is one of it can be a very it can be a high constraint in the safety demonstration with the new referential taking place in France. And also another thing I would like to add about costs is that we have to keep in mind also the cost of all the experimental qualification, characterization of new fuel designs, and that will also depend on the requests of the specific safety authorities that we have to deal with in each country. Some safety authorities can be very demanding and ask a lot of tests, especially in experimental reactors, that can be costly. So at that point, I would say that depending on the negotiation skills of the nuclear operators, maybe we can have not too high costs, but we are aware that it can be a very long process with a lot of uncertainty, and the uncertainty by itself, going along with the licensing process, is part of the global picture we have to keep in mind when we think about costs.
As you mentioned, in France, there's less interest in some aspects of this, and I think that part of it is that because of the reprocessing policy, high burn-ups aren't very attractive in French reactors. But you did mention the issue of ballooning, which is linked to operating temperature. So if you have a fuel that can operate at higher temperatures, doesn't that have an impact on the economics?
Yes, I would say it has an impact on the economics because, of course, it will enable us to demonstrate that our nuclear plants can be operated according to the safety authority requirements. So this is very important to make sure we can, I would say, stay alive. Nuclear plants life extension is a very hot topic nowadays. So, of course, every improvement that we can show may help us towards that objective. But I just wanted to emphasize the fact that I would say it's more like lifetime extension, making sure that we can demonstrate that we can safely operate our reactors as they are, I would say, taking into account new requirements and new fuels, but we don't really ambition longer cycles or high burn-ups. As you mentioned, of course, the reprocessing issue, of course, is determining in this type of strategy. So we don't really we don't plan power uprates also. You see, that's the type of slight distinction I think I can suggest when you compare the approach in the US and the approach in France, for instance.
Thank you. I understand. Mark, do you have any comments on this aspect?
Well, in fact, as Marie already mentioned, indeed the entire life cycle must be addressed. It's probably too early at the moment to assess the economics of the revolutionary concepts that are currently being studied. Although the R&D is aware now, perhaps more than 2-3 decades ago, to identify potential showstoppers on the side of the economics, then that really is at the heart also of the R&D.
Thank you.
Yeah.
Tatiana, anything to add?
Just as you mentioned, that high burn-up and high enrichment is considered as the main trigger in the cost reduction for the fuel production, for the electricity production. And I know that in many countries these are directions, that many countries are moving in these directions to reduce the cost of production electricity.
Thank you. As Kamal mentioned in his presentation, one area that was examined by the expert group in some detail was this issue of compatibility issues between different fuels and different claddings. How important is this to the overall picture? Is this an effect that could be a significant driver in the selection of technologies going forward? So, see who wants to jump into that.
Well, when we look at the evolutionary concepts, when you say about fuel-clad compatibility, for the evolutionary concepts which use the concept of coating, the impact is indeed limited. Coatings on the outer side of the cladding are expected to principally affect only the coolant side effects. Corrosion, hydriding, wear, those things. For the revolutionary concepts, they will impact both dimensional stability, they will impact, and there also the fuel-clad compatibility comes into the picture. Plus, of course, the above mentioned as well. Now, at the moment, currently the research focuses on changes that do not fundamentally impact known reactor operational conditions. We are not changing at this moment. That was not at the outset of this report, to look at concepts that would fundamentally demand different reactor operation conditions. Beyond those stages that are currently already explored. For example, operating BWR at low oxygen conditions in the primary coolant. One may anticipate that, for example, the control rod system design is affected, but that goes beyond the question that you just asked.
Thank you. And I know we have Dr. Corrado online from JAEA. Do you have any comments on those subjects?
You mean on the cost?
Well, let's focus on the cladding fuel compatibility. Do you have any comments on that?
Yes. I guess the most important issue on the compatibility is PCMI and PCCI, pellet cladding mechanical interaction and pellet cladding chemical interaction. And also another important issue is irradiation effect of cladding. So when considering the extension of burn-up, these issues are highly important.
Thank you. It sounded like you wanted to make a comment about the cost, so please feel free if you had something.
As for cost, yes, I guess the situation for advanced fuel is mostly same as cladding. And I guess we should achieve TRL4 level, at least, for the better estimation of cost. Currently, unfortunately, almost all concept is still in TRL 2-3 levels, and so for better evaluation, at first we need to achieve TRL 4 level. That is my opinion.
Thank you very much. We have another question that's come in. The question is from the point of view of safety. What is the safety criteria of ATF, and how do we assess whether ATF fulfills those criteria? Anyone want to attack that one? Marie, sure.
I can try. Of course, we are very much structured, all of us, when we worked on those ATFs by the way we are already working on current fuel designs. But we are aware that when you think about revolutionary designs, some new questions may arise about safety justification. So this is a very, I would say, complex topic. But we can be helped by the global work that can be organized around that topic. I took part in September in a workshop that was led by someone from the NRC, Mr. Clifford. And the aim of this workshop is to produce a technical opinion paper on safety criteria for ATFs. And it was very interesting to see the diversity of the participants from different regulatory bodies and different nuclear operators and suppliers and fuel suppliers and labs. And being led by the NRC, it really gives an impulse to think really safety first in terms of really safety demonstration and not just our feelings. So that type of work can be, it can help to have, I would say, a more shared process within the different safety authority or regulatory bodies, and it could help to converge maybe a little faster on complex issues, because if I know that in each country, once again, safety authorities have their own independence and their own specific focuses, but sharing on that type of topic could help identifying more quickly the proper safety issues, specific criteria that have to be dealt with. When you have different types of materials that we are not used to irradiate in our reactors, it's important to take into account those questions. So.
Yeah, to add on that, for the evolutionary concepts, I think the current regulatory framework is a perfect guideline and has established rules and procedures. For the revolutionary concepts, at the moment we are, so to say, at the stage of separate effect tests research. Obviously, that needs to converge, because at one point in time, the fuel is to be regarded as a system. It's the fuel system. It's not the fuel on its own. It's not the cladding on its own. It's the fuel plus the cladding plus the sealing, and then all the structural parts of the assembly. So as a whole in a core, whether we are today ready to state that we have a regulatory framework for the revolutionary concepts completely and fully understood, that is yet to be developed at the moment. Maybe that our speakers on the other sides of the ocean can also comment on this.
Kamal, Dr. Karada, any comments on that?
I have one comment. In this sense, I guess we evaluated attribute guide spreadsheet, and this is given an appendix in our report. And this attribute guide spreadsheet might be a very, very first baseline on this kind of discussion.
Kamal?
Unfortunately, the attribute guide spreadsheet is very, very working level, but it is very useful, I suppose. Do you have any idea, Kemal?
Yeah, my comment is, I think in terms of the general design criteria, what we put into the attribute guide, it kind of addresses the issues. The specific question whether or not the safety criteria needs to be revised, I think the answer, especially for the revolutionary concepts, is clearly yes. It's the next level of details, because the current safety criteria obviously is very much biased towards what we know about the zircaloy behavior and its interactions with the uranium oxide. So, and that is why I think there is a consensus that any further international activity in this area should be focused on trying to develop a safety criteria for some of these more revolutionary fuels that have very different properties than what we are used to.
Kamal, just to follow up on that, it's somewhat of an analogy to the regulatory frameworks for light water reactors, and how there is a conversation in some countries about developing a different framework for advanced reactors, one that would be technology neutral. Would you? I know you're not a regulator, but would you anticipate that we would need to move in the direction of some sort of technology neutral framework for advanced fuels as well?
My personal opinion, Bill, is yes. I think the level of detail that we had in the safety criteria for zirconium is going to be almost impossible to achieve with these different materials. I think we got to go to a technology neutral, general design criteria type of a framework, and have the vendors demonstrate that they meet that criteria, and not necessarily have very prescriptive in terms of how it is that you have to demonstrate to meet that criteria.
Marie, you've made the point that different national regulators have different approaches and frameworks, but this sounds like an issue that could be dealt with on a more generic basis. Do you think that trying to develop these general criteria in a technology-neutral framework is something that lends itself to a multinational approach, or do you think this really gets back to individual national regulators?
I think that if we manage to do that, it would be a great step, because frankly speaking, for example, when we consider a different type of material for the pellet, it already raises some questions, because typically when we just change the cladding, it's already a step that can be that involve considerable effort in terms of licensing. But sometimes we can rely on some tests if we just change the cladding but not the pellet. For example, taking a regular uranium pellet or taking a doped pellet, that's a new pellet. If you just consider a regular uranium pellet and then you change the cladding from one material to another, like we are already doing in the current nuclear world industry, you can rely on same, for example, RIA tests, which are very costly. We can make some demonstration for the safety authority, ensuring the qualification of this new fuel, because we already have an RIA test with the same type of pellet, and we just change the cladding. Now, if we change also the pellets, for example, going to doped pellets, we probably need to perform the whole set of tests again. So if some way we manage to find a process that would enable us not to complexify the safety demonstration according to each type of material within the core, it will be, from the point of view of the industry, nuclear operators, it will be very convenient.
Well, to to comment a little bit on that, for general design levels, absolutely yes, there might be an effort coordinated to technology neutral. But once you go one step deeper in the detail, it will be difficult, if not impossible, I would say, to remain technology neutral. One example can be fission gas release, which for light water reactors is a concern. Well, if for the sodium fast reactors in the past, it was not a concern because by design it was considered to operate under 100% fission gas release. For materials test reactors, it's by materials choice and operating conditions never possible to have fission gas release. So there, at one level deeper, whereas in one design you do have an issue, because there is partial release and you would like to understand and be able to quantify that partial release in order to optimize your operational conditions to the best possible way. Well, it either disappears by the operating conditions, material test reactor, or it is 100% and release already from the design, and it's also not a problem. So if it's 0 and 100, it's not a problem, it's a problem in between, and that's technology dependent.
That's a very good point. But it does get to the question of what criteria would you select and how would you characterize them. This obviously would be something that would take a lot of work. And I think we ran into many similar issues when it came to trying to find general approaches to advanced reactor technologies. As you say, as you drill down closer to the technology, very specific issues come to the floor. Yes, please, Tatiana.
The NEA is now trying to establish and to address this issue, and the Committee for Safety of Nuclear Installation is establishing a new group that will identify safety requirements to the ATF new fuels, and also the expert group that released the reports that we are talking about is thinking about how to continue with the activity, and the requirements from the group participants is that we need to identify the issues that are triggered and that are triggered by the safety requirements. So we are working on this direction together with safety, and I hope we'll have valuable results.
Tatiana, since you picked up the microphone, there's a question I think I'd like to have you start with. And it's a question where it states, it's been mentioned that as development and deployment of ATF will require high fidelity and credible experimental data, such experiments in material and test reactors would be very expensive and complex to perform in all but a few countries. And so how do we go about getting access to those facilities for experiments? And is there a way of establishing an international, multinational partnership to do that? I know this is something you've been thinking about a lot.
Yes, it's true. The Nuclear Science Committee initiated, several years ago, initiated a new activity on the development on experimental support, enhancement of experimental support for fuel development. And also the review of needs performed within the initiative called ENI 2050 also identified the fuel development as a key needs for innovations. And we've been working last year identifying the facilities that can address the experimental needs, in particular experimental needs to address experimental needs for accident tolerant fuels. Nuclear Science Committee, together with the CSNI, organized the 2 workshops this year in January and October. And we have participants from many countries representing fuel vendors, the utilities, representing the research organizations, and their safety organizations. And the consensus was it was a very fruitful discussion. And there was a consensus that we need to establish an international framework that would facilitate the access to the research reactors, because research reactors are continuing to play key role in the addressing experimental needs. And currently we are establishing this framework, and there are several facilities that look very promising to be a key part in this framework. And these facilities, after the closure of Halden reactor in June, these facilities are BR Reactor in Sikasen and in Belgium, the MB reactor in Russia, treat and ATR facility at INL, and also the Cabri reactor in France, and in future it will be Jules Horowitz reactor.
No, yeah.
Jules Horowitz reactor.
Yes.
So we are now working with all this, the representative of these facilities and the participants of the workshop to establish this framework, to identify the needs. And we work together with safety to identify the needs for safety too. I hope at the beginning of the next year, we have several proposals for the joint projects. And I hope that then at the beginning of the next year, we will have a meeting discussing the concrete joint project proposals, and we'll go ahead with new joint project. We'll try to address the issue that we have due to the closure of the Halden reactor.
So as you're suggesting that under such a framework, an institution that wanted to perform an experiment could come into this project and get access to these facilities and understand where to go and how to go and be able to get access and put an experiment into the reactor.
Yeah, within this framework, the access is very important to provide access, but also I think we can use this opportunity to change the paradigm to the design of experiments, and we will try to work together on the design of the future experiment and on the analysis of the experiments, which is very important. And another important aspect is to the data preservation, how we preserve the data, how we analyze, treat the data, to make them useful, to transfer the data from raw experimental measurements to the quality that can be used, the quality that can be used for validation of high fidelity codes, for fuel performance codes.
Okay, thank you. Mark, did you want to add something?
Yes, well, we have seen in the course of the last couple of years that the research capacity has been reduced with closure of reactors, France, in Japan, and recently this year in Halden as well. Now, this being said, there still is research capacity in OECD and non-OECD countries, which is used and deployed for ATF tests and research campaigns as we speak on both sides of the ocean. There is international research still ongoing, so that is not stopped by the fact that there is a reduction in research capacity. And as Tatjana, as you said, indeed, there is now, with the recent closure of the Halden reactor, there is an awareness that we still have research capacity, but it is significantly reduced. The research as it was done in the reactors that were recently closed will need to be redefined, because the operating conditions are different in each of the material test reactors. So there is a necessity of rethinking several of the experiments, working with more or lesser instrumented irradiations, more frequent, less frequent post-irradiation examinations, larger dimensions, smaller dimensions of samples. They will be that will necessitate a new approach for several of the ongoing projects that were in the Halden reactor, but it's not impossible to continue searching for a solution to the research question. It will need a rethinking of the approach. Does not mean that the research objective itself cannot be met. So that is.
Particularly for the advanced fuels, though, I would expect that there are some experiments that would be very difficult to perform in existing facilities. There are some experiments for fuel failure experiments, for example, where we were looking at dirty loops. I don't know of any facilities that can do that today. So there are some tests we don't have the capability to do with the loss of Halden. But in the future, Jules Horowitz, I think, offers the possibility to do some of these things. But right now, there is a gap.
As I said, the platform on which in reactor tests can be performed is still there. The reactors are still there at the moment. What they do lack is the specific test capacities already installed and operational. So nobody was especially anticipating the closure of the Halden reactor this year in the middle of the year. So there was no, the research community was not prepared for that. And there is no need to have a copy of everything in every test reactor unoccupied, so to say. We have different approaches, we specialize. So if it would have been anticipated a bit better, then I'm sure that the capacity would exist as we speak. It will need the time it needs for an installation to bring it operational in another test reactor. It will need a rethinking of some of the experiments, but the basic infrastructure still exists.
I agree with that. And that's a point that we certainly made before Halden was closed, that if the community had had 2 or 3 years to prepare, some of these loops could have been built into existing facilities, and it wouldn't have been as disruptive. But nevertheless, we are where we are, and we'll have to bridge the gap as best we can. Kamal, or did you want to make a comment about that? No, this isn't a subject that you have been thinking about.
Well, part of it is, as Mark said, I think we will have to bring up the existing infrastructure up to par to meet some of those needs. But again, part of it also is rethinking exactly how we do the experiments and changing the paradigm and doing smarter experiments combined with modeling and simulation and advanced instrumentation to answer the same questions that we were able to answer in the past with what I would call brute force prototypic experiments. So it does give us, we have lost some capabilities over the years. Some of it still exists, but it also gives us an opportunity to maybe rethink the way we do fuel qualification. So.
All right, we're very close to the end of this, and I want to maybe give each of you 30 seconds or so to make a final comment about anything about this report that you would like to highlight. And Dr. Kurata, I think I'll start with you.
I'd like to emphasize is I would like to point out the very importance on the second phase of EGATFL. After today's discussion, we already identified several important issues, and I guess to continue the second EGATFL, this kind of activity is very useful for international. That is my comment.
Thank you very much. Kamal?
Well, since I had the opportunity to give the summary of it, and I tried to highlight the important parts of it, but the big item at this point is really trying to continue some sort of an international collaboration in this effort recognizing that the fuel vendors are also going full speed ahead, and there is a lot of new data being generated out there that is not necessarily accessible by the research organizations. There are proprietary data, so I think the next phase is going to be continuing this effort without necessarily overlapping with what the fuel vendors are doing.
Interesting point. Marie.
I did not expect such a great experience. I must say, when we launched the EGATFL, it turned out that it was a very important collective work. Everybody was really involved and committed, and it worked really well. I was surprised because we didn't necessarily knew each other before and so on. But what I have in mind is that this report, as great as it is just like a photography of the information we had at the time. But there is also a lot of dynamics, as Kemal just pointed, in this area. So this photography, for example, when you take a look at the TRL table, it's very static, actually. But the real world, it's not like that. So for that reason, I think it's very important that we keep exchanging and keep an updated knowledge shared on that topic.
Thank you very much. Mark?
What I especially would like to take with me from this exercise that we did is the integrated approach, where we had the opportunity and to work together as research organizations with utilities, with the licensing authorities, and with the and to approach the problem from all sides. And whereas in many other approaches it is more sequential, here we really integrated this effort, and that's something that we already were living during this report, and we're taking that approach with us also in another setting. NI 2050 is also gave this this approach as really the way forward to perhaps sometimes we are using the word acceleration, but I would rather say to integrate the research better.
Thank you very much.
In this report, as you know, there is a description of the experiments that will required for the development of ATF, and this will be a very valuable input for further development and enhancement of our activities that we are building at the NEA on the support of the development of innovative fuels and materials, including the accident tolerant fuels, and I think it will be extremely valuable input.
Excellent. Well, again, thank you to all five of you and all your colleagues who worked on this important report. And as Marie's indicated, the work must go forward. So we continue to look forward to collaborating with the whole community. And I will hand the floor back to Andrew.
Thank you. We'd like to remind you that the report is available online and can be downloaded from the NEA website at www.oecd-nea.org. For more updates and news, we also encourage you to follow us on the social media where the NEA is present. And you can find the NEA on Facebook, Twitter, and LinkedIn. Thank you.